Morning. Very well, we have already started the discrete time Fourier transform, as you remember. And we have seen some examples about what sort of outcomes it will produce. Let's briefly remember some of the properties that we already know about the discrete time Fourier transform. Perhaps the two fundamental properties are its representation, its notation is like this: x of e to the j omega. That is the notation. So please don't confuse it with the Fourier transform of continuous time signals, which are indicated by capital X or whatever signal it may correspond to, of j omega in continuous time. In discrete time, the Fourier transform is notated like this: capital X of e to the j omega. And from this notation, we understand that everything, the Fourier transform, every Fourier transform is 2 pi periodic in omega on the frequency axis. When you plot it, it must correspond to some 2 pi periodic signal. So this was the last example that we have seen. It was a rectangular pulse of x of n. And its Fourier transform is again 2 pi periodic. It happens to be. Let's continue with another example. And this example is somehow briefly related with the previous one, but you may guess the answer already. How come it is related with the previous one will be an issue. Suppose that you have this signal, x of n is defined to be the unit sample or the unit impulse in the center, delta n. Do you remember what the Fourier transform was for the continuous case? What was the continuous time Fourier transform of delta t? Do you remember that? It was 1, which covers all the frequencies equally. And it's again 1 here. We will have the same thing. Or maybe I should write down the answer first. That is equal to 1. But if you just evaluate the integral, or the summation, how come it works out that way will be a problem. The discrete time Fourier transform, if you evaluate using the formula, will be equal to this: sine of pi n over pi n. Or you can think of it from the answer to the previous question. Look at the previous answer that we see, this one, which was the Fourier transform of a rectangular pulse. The Fourier transform seems to be sine of omega in parentheses n plus 1 over 2 from minus n to plus n. Okay, so what is minus n and what is plus n? Over sine of omega over 2, of course. So what are these entities that we have? In the previous case, n is equal to 1. N is equal to 0. It's not even 1. So what you will have will be, perhaps I shouldn't write it this way. I should copy this formula, which is sine omega n plus 1 over 2, sine omega n plus 1 over 2 divided by sine of omega over 2. Okay, so this was the discrete time Fourier transform. And what we have here is for n is equal to 0, because it is from minus 0 to plus 0. It is only one pulse, unit sample. You can think of it as a very narrow rectangular pulse, okay, consisting of a single sample in the center. And when you do that, the numerator will become sine of omega in parentheses 0 plus 1 over 2, which is sine of omega over 2. And the denominator is also sine of omega over 2. Therefore, you will have sine omega over 2 over sine omega over 2, which is equal to 1. So you can even extract it from there, or you may use the formula for the discrete time Fourier transform. Whatever you do, you will come up with this formalism, and that is equal to 1. Is it 2 pi periodic is a question, and the answer is clearly yes. It is everything periodic. It's a constant signal. Therefore, it's also automatically 2 pi periodic as well. It's staying the same everywhere. So it includes all the frequency harmonics, including the low frequencies, mid-ranges, and the high frequencies, all equally. It's all 1. Now, an interesting consequence that you may derive from here is the inverse Fourier transform of it. So the question is now, what is the inverse discrete time Fourier transform of 1? Are we able to obtain the impulse? Let's call it x hat of n. We don't know whether it is an impulse or it's equal to x of n yet. Of course, it must be that way. But let's apply the formula, which will be an interesting thing. From minus somewhere to plus somewhere, it's all ones, e to the j omega n, and this including the w's, or if you keep the integration limits as flexible like this, you will have this thing to be sine w of n divided by pi n. This is the integral that we will get. And here you must decide from where to where you need to take the integration. It is once everywhere, so it must start from minus pi and go up to plus pi. So this must be minus pi and this must be plus pi, which makes this w to be equal to pi, and therefore it's automatically sine pi n over pi n. So we found the answer to be sine pi n over pi n, not the unit impulse. Or is it unit impulse? Is the next question. It's the next step. Does this correspond to a unit impulse? It's not very obvious to see that this is equal to a unit sample in discrete time or not. The trick that you must see is sine pi n is equal to 0 always, because it's an integer multiple of pi, including 0, n is equal to 0, n is equal to 1, n is equal to 2. For all n, sine pi times n is always on the horizontal axis when you rotate. It's either here or here or here or here. But whatever position you have, either this place or this place, the vertical crossing of that would correspond to the sine, and that's always 0. Sine 0 is 0, sine pi is again 0. Sine 2 pi, 3 pi, they're all zeros. So sine pi n is equal to 0 always. It seems to be a 0, but look at the denominator, it's also pi n, which is also 0 when n is equal to 0. When n is equal to 0, pi n is 0, sine pi n is also 0. So you apply the Hospital's rule, and there is a shortcut for using sine in the Hospital's rule, as I said. You can just eliminate the sine factor from there. Just eliminate it, and you have pi n over pi n. In other words, sine theta is equal to theta for small theta. And n is 0 is a very small theta. So pi n over pi n is what you get. They cancel each other and you will get a 1. So at n is equal to 0, this ratio is 1. For all other n's, the denominator is different from 0, but the numerator will always be 0. So we can say that this thing is equal to 1 when n is equal to 0, and 0 for all other n values. which is automatically equal to an impulse. So we say yes, they are equal. Interesting formula to represent an impulse, isn't it? Sine pi n over pi n. That is an impulse. It is non-zero, which is 1, only at n is equal to 0. For all other n's, it is 0. So this is a verification of the inverse Fourier transform of 1, which is literally impulse. And that's in accordance with our previous observation saying that x of n is equal to delta n will produce a Fourier transform of x of capital X of e to the j omega equals 1. So everything is now compatible with each other. They are in accordance. And that's an important example. The next example is now we are starting to see examples regarding periodic discrete time sequences. Before the example, let's remember what we were doing in the continuous case. Do you remember how we were finding the Fourier transform of continuous time periodic sequence? If the periodic signal is continuous, if the continuous signal is periodic, let me put it that way, if it is periodic, then the Fourier transform concept is not through the formula. It's through the Fourier series. Do you remember that? For periodic signals, we have Fourier series. It's always the case. So we have to, again, consult to the Fourier series representation. In the continuous case, we were finding the Fourier series coefficients. For example, what were the Fourier series coefficients of a cosine? The Fourier series coefficients of a cosine of omega 0 t, for example. Yeah, they are all 1 over 2 and 1 over 2. One of the 1 over 2's correspond to a frequency of omega 0. The other one corresponds to a frequency of minus omega 0. They were the harmonic frequencies and the coefficients were 1 over 2. So what we were doing was putting two impulses at the positions of the Fourier series coefficients. With the magnitude, Fourier series coefficients are ak, let's say, we put the impulse magnitude to be 2 pi times ak. So the Fourier series coefficients were 1 over 2. The impulse values were 2 pi times 1 over 2, which is pi. Pi here, impulse, pi here, impulse at omega 0 and minus omega 0. We are going to do the same. We will find the Fourier series coefficients. We will evaluate the corresponding frequency of those Fourier series coefficients. And then we will insert impulses there. The impulses will again be multiplied by 2 pi. It's exactly the same operation that we need to do. Let's see the example now. X of n is equal to e to the j omega 0 n. And let's assume that this omega 0 is a 2 pi rational. Okay? Like 2 pi over capital N, for example. So it has a period of capital N, therefore a frequency of omega 0. It's a pure harmonic. It's even simpler than a cosine. A cosine has two harmonics at the positive and negative frequency. This simpler, primitive sinusoid has only one harmonic at omega 0. So we say that A1, let's call it, is equal to 1. Isn't it? It's only a single harmonic. There's no other harmonics. So what we need to do is we need to draw an axis of frequency and indicate what that omega 0 is. Let's assume that omega 0 is here. So we put an impulse here whose magnitude is 2 pi times 1, which would automatically make a 2 pi because the Fourier series coefficient was 1. So we insert this impulse in the position of the Fourier series coefficient. If you have a minus 1, then you are supposed to put a 2 pi sort of thing at minus omega 0. Not only omega 0, but minus omega 0 too. So this is omega 0. But we do have a problem now. This representation by itself is not enough. Why is it not enough? Why isn't it the correct solution? So I say that it's only partially correct and it's not sufficient because it violates the first condition that I have indicated. I have even mentioned it in the beginning of this lecture. Do you remember that? The Fourier transforms of discrete time signals should be 2 pi periodic. This is not 2 pi periodic. This is only a single impulse. So the issue is also related with the Fourier series coefficient relation for discrete time signals. Do you remember that the Fourier series coefficients are not single in discrete time? It's not only a1 which is equal to 1. It is also a n plus 1. You remember that? A n plus 1 is also equal to 1, or a 2n plus 1 is also equal to 1. It goes on like this. So we must put impulses in their locations too. We must have a periodic extension of impulses. Luckily, the position of an plus 1, the harmonic frequency location, it looks complicated. What frequency is that? It is omega 0 plus 2 pi. Simple. 2 pi plus omega 0. Suppose this is 2 pi. Therefore, at 2 pi plus omega 0, we have the same impulse. So this is the impulse coming from here. This is the impulse coming from here. We also have, of course, 4 pi and 4 pi plus omega 0 is here. So this position is 2 pi plus omega 0. This position is 4 pi plus omega 0. And it comes from the third. A similar situation is valid for the negative side frequencies as well. If this is minus 2 pi, then around here we must have minus 2 pi plus omega 0, 2, which corresponds to a of minus n plus 1 is equal to 1. So they are repeating themselves. Or you may attack the problem like this. Let's forget about everything. Let's only find the original value, a1, that one. And then you have to just replicate it to make it 2 pi periodic. If it is at omega 0, it must also appear at 2 pi plus omega 0, 4 pi plus omega 0, 6 pi plus omega 0. It must be extended to become 2 pi periodic. Okay? So this is the correct plot of the Fourier transform for x of n is equal to e to the j omega 0 n. If you want to write it, I may ask the question in 3 ways. I can ask you to plot it, I can ask you to write down the mathematical expression, or I can ask you to indicate both. Both write down the mathematical formula and the plot. So if the question is write down the mathematical formula for the Fourier transform x of capital X of e to the j omega, not with a plot but also with a mathematical expression like this. Can you write it? You should develop the necessary skills for impulse trains. You already encountered a question like that in the first exam. This is an impulse train. So the expression is the scales or the magnitudes are always 2 pi. So let's write the 2 pi there. It must be in the form of an infinite summation. K from minus infinity to infinity. And it is consisting of impulses. What is the first impulse? The first impulse is omega minus omega 0. It is at omega 0. And now we must replicate it with a period of 2 pi. So we must write it with a minus 2 pi k. So at k is equal to 0, it will be delta omega minus omega 0, which is the original impulse that we found. At k is equal to 1, it is the next to the right. At k is equal to 2, it is further next to the right. At k is equal to -1, it is to the left. So k ranges from -infinity to infinity to 2 pi periodically replicate all these impulses. You must make yourselves familiar with this kind of representation of impulse train and how it looks like. Or vice versa. If something looks like that, can you write the mathematical formula for that repeating pattern? If the repeating pattern is an impulse, it's an impulse train. If the repeating pattern is a triangle, it will become a triangle train. Then you have to write the formula of the triangle here instead of delta, and it must repeat itself like this. Okay, that's mathematical way of plotting infinitely repeating periodic sequences. You find first the repeating pattern, you formulate it, and you put a summation to make replicas of that by putting minus the period times k. The period for this case is 2 pi, of course, so it is minus 2 pi k inside the delta. All right. Now this thing is also, it's not the only example for the Fourier series coefficients. For a single Fourier series coefficient, you may have more than one Fourier series coefficients. You see that all the Fourier series coefficients, the originals, how many original or distinct Fourier series coefficients are there in a periodic discrete time sequence? At most by the number of the period. If it is capital N, for example, you have capital N distinct Fourier series coefficients. They must fit into a width inside this plot of 2 pi. From 0 to 2 pi, you can say, or from minus pi to pi. You plot those distinct Fourier series coefficients, scale them by 2 pi, and they will become the Fourier transform, and then repeat them at 2 pi. Everything will have to fit into 2 pi, the width of 2 pi. Now, a nice verification is, it's a check, we can say, is the inverse Fourier transform of this Fourier transform equal to e to the j omega 0 n. These checks will also constitute some examples for the inverse Fourier transform questions, because it's not only the Fourier transforms that I may ask. I may ask you the inverse Fourier transforms as well. So the question, let's consider it like this. Look at the top plot, or the mathematical expression of x of e to the j omega. What is the inverse Fourier transform of it? You must tell me the inverse Fourier transform is x of n is equal to blah blah. And for this case, x of n is equal to e to the j omega 0 n. Can we show it, or can we derive it? For that, we will consult with the formula 1 over 2 pi within a period of 2 pi x of e to the j omega, which is the Fourier transform that we have, times e to the j omega n d omega. This is the formula. Now let's apply the formula. But you see, x of e to the j omega is infinite series. There are infinitely many impulses, 2 pi periodic. But look at the integral. The integration limit is limited to 2 pi width only, which means we have to take only one of those impulses. For example, if we say this 2 pi sequence is from 0 to 2 pi, then which sequence or which impulse will be inside the integral limits? It's only this impulse, the original impulse. It will be inside the limits. So we will have 1 over 2 pi integral from 0 to 2 pi, and inside it we have only one impulse, and that one impulse is this. with a scale of 2 pi, of course, e to the j omega n d omega. We automatically see that these 2 pi's will cancel, and we will have from 0 to 2 pi e to the j omega n delta omega minus omega 0 d omega. And this is the integral that we need to evaluate. Now, when you multiply something with an impulse, you have to be careful, but the answer is easy. This impulse forces omega to be only omega 0, because the impulse is non-zero only at omega is equal to omega 0. For all other omega values, omega 0 plus epsilon, omega 0 plus 2 epsilon or minus, they are all zeros. The impulse forces omega to be only omega 0 because it's non-zero there, which means that in the multiplication term with all the other expressions, the other expressions must automatically make omega is equal to omega 0, nothing else. Because for all other omegas, again, the impulse is 0. And they will not contribute to the integral. So this integration is equal to e to the j omega 0 n delta omega minus omega 0 d omega. This omega becomes omega 0, because for all other omegas, they will not contribute anything. Now, since it is an e to the j omega 0 n, naturally it is independent from omega and can be taken out of the integral. E to the j omega 0 n integral from 0 to 2 pi delta omega minus omega 0 d omega. And therefore we only have one integral term now, and that one single integral term is the integral of an impulse, and we know that the area under an impulse, wherever it may be at omega 0, it may be at 0. Anyway, the area under the impulse is always 1. So we have e to the j omega 0 n, which was the original question. This was the signal, if you remember. Right? So we found the inverse Fourier transform and verified that the inverse and forward Fourier transforms come up with the same things. Look at the original question. E to the j omega 0 n. Alright, so how can we generalize the Fourier series coefficient impulse insertion thing? The general relation, we can say it like this. If x of n is periodic, then we can write x of n as a linear combination of capital N Fourier series coefficients scaled by harmonics, ak times e to the j k omega 0 you can say, or you can say 2 pi over capital N n. So this 2 pi over capital N is omega 0, the fundamental frequency. So we can always write it like this. Therefore, the Fourier transform corresponding to this expression is k from minus infinity to infinity 2 pi times a k's will be there, and at the position of this harmonic we will have an impulse. What is the position of this harmonic? The position of that harmonic is omega minus k omega 0, let's say k times 2 pi over capital N. That is the position of the maybe I'm doing it a little bit in a hurry. We need two summations, excuse me about that. One of them is k within a capital N, and this much of the expression, if we close the final parentheses, will correspond to putting capital N Fourier series coefficient impulses, rendering them on the plot. And inside the plot, they will be, I don't know, from 0 to 2 pi or from minus pi to pi, with a width of 2 pi. They will be rendered. Okay? Now we have to further replicate all these impulses to become 2 pi periodic again. So this is only capital N of them. To further extend, I need to put another summation, L from minus infinity to infinity, and put it like this, 2 pi L. So this will be the discrete time Fourier transform. If you want to plot it only, if I ask you to plot the Fourier transform, the easiest way to attack is to consider this portion only, which corresponds to putting one impulse per one Fourier series coefficient first, within a range of 2 pi, and capital N of them must be there, as long as they are non-zero, of course, and then extend them by 2 pi here. Repeat them to make everything 2 pi periodic. And the mathematical expression happens to be like this. Graphically illustrating the whole phenomenon, what I expect is, this is too narrow, something like this. Suppose that you have A0 position, A1 position, A2, A3, A4, and A5, and A6. Okay, so it's periodic by 7, in other words. You first plot everything. This is 2 pi, this is 0, this position. At 0 you put A0, at 2 pi over 7, or 2 pi over capital N, you put A1. At 2 times 2 pi over 7, or 2 pi over capital N, you put A2, A0, A1, A2. They are all multiplied by 2 pi, of course, 2 pi A0, 2 pi A1, etc. And you render everything. And you leave open the 2 pi point. Why? Because at that point, it will be equal to A0. The original will come there. And everything will repeat itself. And then, let's choose a different color. We repeat all these impulse values like this. Another replica with the reds this time. You can make another replica with the greens, etc. They are just 2 pi repetitions. So when you try to plot these things, this is what you get. And this 0 point will be identical to the 2 pi point, and it will be identical to the 4 pi point as well. They are just repeating themselves. Everything is 2 pi periodic, even the impulses. So in general, we can think of it like this. If you have a periodicity in your signal, you expect an impulse in the Fourier transform. It's the same for the continuous time. It's the same for the discrete time. If you have a periodicity, you must find an impulse. Now, can you visualize this thing? Can you motivate this fact to yourselves shape-wise? What does that mean? When we have an oscillation, the Fourier transform will have an impulse. What does that mean? It means something like this. In telecommunications, if somebody is transmitting some frequency, harmonic, a sinusoid, when you look at the spectrum, which corresponds to the Fourier transform, the magnitude of it, you see a huge value at that frequency. That corresponds to a station, basically, a radio station. a lot of power is injected into that frequency. That is meaning that the Fourier transform has an impulse corresponding to the frequency. And it happens only for periodic or cyclic signals. Whenever there is a periodicity or cyclicity, then the Fourier transform must have an impulse. So if ever you see an impulse in a Fourier transform expression, suppose that I'm asking the inverse Fourier transform of something, and I'm plotting it. I give you figures. You recognize that in the Fourier transform there is a sinc shape. Very well. The sinc shape is there. But there is also an impulse, or there are two impulses. What kind of an inverse Fourier transform do you need to apply? For the sinc Fourier transform, you will say that, okay, I know the time signal. What's the time signal? It's a rectangular box. How about the impulse? The impulse indicates that there is a sinusoid with that frequency. So what is the time signal then? The time signal is a summation of a rectangular box and a sinusoid. So it's a sinusoid increasing at the position of the rectangular box and then decreasing back to around 0, for example. Let me give you that, let me illustrate that a little bit more in detail like this. Suppose that on the frequency axis you have this sinc shape and then an impulse here, another impulse here. So this is x of j omega. Okay, I'm talking about continuous time Fourier transform. Why am I doing that? Because I don't want to cut it and repeat it to make it a discrete time Fourier transform. The only difference between the continuous and the discrete are the discrete one must repeat itself in 2 pi periods. This is not periodic, okay, it's normal continuous time Fourier transform. So what is the x of n? X of t corresponding to this? X of t corresponding to this will be a combination of a rectangular box, because the rectangle's Fourier transform is that sinc. But from the linearity property, if the Fourier transforms are combined, then the time signals must also be combined. There must be a cosine term as well. And the cosine term, let's assume to be like this. The red one. So the combination of the red and the black will probably look like this. I'm sorry about my drawing. I'm not very keen on plotting things. But something like this. I'm just trying to add up a rectangular box and the sinusoid. Okay. The rectangle will push everything upwards at an abrupt position, starting from here to here or whatever. Okay, that's what I'm trying to emphasize. So this is the time domain signal that you may expect. So you may combine, and usually the combinations are with sinusoids, and those sinusoids will impose impulses in the Fourier domain. If you see an impulse in Fourier transform, its inverse Fourier transform is a sinusoid. It may be a complex sinusoid, it may be a sine, it may be a cosine, or with some phase, whatever. So this was one indication. The last two examples, the one before the last is this one, which is a simple case. It's a cosine omega 0 n. Let's give a name to that omega 0, 2 pi over 5 n. What is the Fourier transform of this? And from the Euler's expansion, this is 1 over 2 e to the j 2 pi over 5 n plus 1 over 2 e to the minus j 2 pi over 5 n, and we see that the Fourier series coefficients are a1 and a minus 1, which are 1 over 2, we already know it. But the frequencies corresponding to these harmonics are 2 pi over 5 and minus 2 pi over 5. Okay, these are the frequencies of these harmonics. So what we are going to do is we draw the Fourier transform. For real, we can just draw it as it is. If they are complex, you must do something. You must either find the real part or make an absolute value or magnitude operation. The omega 0 is, this is, let's assume 2 pi, and therefore this is minus 2 pi. 1, 2, 3, 4, 5. Let's assume that this position is 2 pi over 5. At 2 pi over 5, I have an impulse, which is omega 0. At minus 2 pi over 5, I have another impulse. Minus 2 pi over 5 is here. And the magnitudes of these impulses are 2 pi times 1 over 2. The Fourier series coefficients were 1 over 2. So they are pi. Pi and pi on the frequency axis. But of course I'm not finished. From here on I must extend everything to be 2 pi periodic. So let's take this origin symmetric thing around 0 to around 2 pi to around 4 pi to around minus 2 pi, etc. So I need a replica around 2 pi like this. If this is 4 pi, for example, I have these impulses as well. Around 2 pi, I have these examples as well. And they are periodically extended now. Everything is 2 pi period. This is the Fourier transform of a cosine. It's not only 2 impulses, it is repeated 2 impulses. Very well. Now is the last example before the break. It's a periodic signal, but the periodic signal is strange. Again, it's a discrete time impulse train. Delta n minus k times capital N. Now, what is the period of this periodic signal? Is this a periodic signal? Yes, it is. It is repeating itself. What is the repetition rate? N, capital N. That is the period. So the period is capital N, and therefore the fundamental frequency is 2 pi over capital N. So what is this? Sorry. So period is equal to capital N. Fundamental frequency is equal to 2 pi over capital N, and that is omega 0. I'll take it as omega 0. Do you remember the Fourier series coefficients of this signal? The Fourier series coefficients, if you don't remember, please check back your notes. They happen to be the same. 1 over capital N. Okay? For all k. So it's not 1, but it's 1 over capital N. Now from here, what sort of an extension can we think of? If they are all 1 over capital N, how can we plot them? How can we represent or express the Fourier transform? Let's try to first express it mathematically. That one must be equal to 2 pi times 1 over capital N. Okay. What was the fundamental frequency? It was 2 pi over capital N, so there must be an impulse at fundamental frequency, which is omega minus 2 pi over capital N. This is one coefficient. But it's not only that, plus 2 pi times 1 over N delta omega minus. At twice the fundamental frequency, there must be another harmonic, 4 pi over capital N. And then we have 2 pi 1 over N delta omega minus 6 pi over capital N plus etc. How many of those etc's do we have? I mean, just to formulate the region between 0 and 2 pi, or within a range of 2 pi, how many Fourier series coefficients do we have? We have capital N of these. Because within a range, within the first period range, we have capital N Fourier series coefficients. That is the period of the signal. We have capital N harmonics only. And all of these are in a 2 pi range, from 0 to 2 pi, for example, or from minus pi to pi. Within that range, we have capital N of these impulses, and they are here. Here they are. All these impulses now must repeat themselves with 2 pi. And when we try to draw that, an interesting thing happens. It's like this. 2 pi over capital N is the magnitude of all the impulses. This magnitude is 2 pi over capital N. And the next one is separated by 2 pi over capital N. And then the next one is at twice of that, which is 4 pi over capital N. And then 6 pi over capital N. And it goes on like this. And suppose this is 2 pi here. The situation happens to be like this. This is 2 pi minus 2 pi over capital N position. At 2 pi, sorry, let me draw it with a red. The next repeating pattern comes. So this 0 point will repeat itself, and then the other one will repeat, the other one will repeat, etc. But as you see, if you just try to formulate everything, it happens to be a periodically repeating impulse train separated by 2 pi over capital N only. We have capital N of these, and then they are repeating themselves. But the formula for the whole picture from minus infinity to infinity is a simple repetition of impulses with a period of 2 pi over capital N. So the formula I can write even more simpler. X of e to the j omega is equal to 2 pi over capital N, which is the magnitude, summation k from minus infinity to infinity, delta omega minus 2 pi over capital N times k. Simple, finished. I don't have to extend it in 2 pi or anything. It is already extended because the structure of the black impulses are not changing in the red impulses. They are just repeating themselves. We found a similar result in the continuous time. The Fourier transform of an impulse train was an impulse train on the omega axis. Okay. Just check back your notes. And now we have the same situation. The Fourier transform of this impulse train is another impulse train, which is this impulse train. Even for the discrete time Fourier transform, they are the same. They are not the same, but it's another impulse train. The fundamental difference is between the periods of these impulse trains. The period of the impulse train in time domain is capital N. The period of the impulse train in the frequency domain is 2 pi over capital N. So if N is larger and larger in time domain, it makes these impulses nearer and nearer. Or if N is smaller and smaller, if the impulses are nearer and nearer in the time domain, then in the frequency domain, these impulses will be far and farther away. They are inversely proportional. You make the impulse train narrower in one domain, you make it wider in the other domain. Okay? They are inversely proportional. But they are both impulse trains. This is also valid in continuous time. Okay? Please do remember your continuous time Fourier transform notes or continuous time Fourier series notes. Okay? We have already covered this kind of an example over there. So while you try to digest what I'm talking about, that's an important and critical issue, by the way. We can give a break. After 15 minutes, we will continue with the next hour.